The new theory that we are going to study is crystal field theory. Crystal field theory was introduced to remove some of the limitations which we were experienced in VBT. So let's see what crystal field theory is all about, what are its assumptions and what are its conclusions. First assumption of the crystal field theory is the metal ligand bond is considered to be purely ionic. VBT was the complete opposite. VBT considered the metal ligand bond to be purely covalent. In CFT, crystal field theory in short form is also known as CFT. In CFT, we consider the metal ligand bond to be purely ionic. In that, if the ligand is an anion, it is considered to be a point charge. And if the ligand is a neutral molecule, it is considered to be a dipole. And if the ligand is a positive or a cation, then also it is considered as a point charge. So now what happens is, first of all, in this case, when we had talked about our d orbitals, the axial and non-axial d orbitals, in this case it comes into play. That is the axial nature and the non-axial nature of the ligands. First of all, what happens is, when the ligand it approaches the metal atom or the metal ion, then the metal atom has axial orbitals, d orbitals, it has non-axial d orbitals. So I will make that. So this is the axial d orbital, dx square minus y square, and this is the non-axial orbital. Now when the ligand is approaching the metal atom, what is happening? The ligand is very far away. So if the ligand is very far away, then the field of the ligand is spherically symmetric. Okay, let us understand that with the help of an example. Let's say there are 5 kids. Okay, there are 5 kids and 2 of them are standing a little separately and 3 of those 5 are standing a little separately. Now from far away they are seeing an ice cream seller come towards them. Okay, so what is going to happen? All of them are going to get excited because they don't know. Right now they don't know who the ice cream seller is coming towards. So all of them are going to get excited like, yeah, we are going to get ice creams. But when the ice cream seller comes closer, he approaches closer, then it becomes clear that the ice cream seller is coming towards 2 of those children and it is not coming towards 3 of those children. When the ice cream seller was far away, we can say that the ice cream seller is the ligand. So the ligand has a spherically symmetric field. Okay, so if the ligand is approaching the orbitals, then all of the orbitals are getting excited equally, whether they are axial or whether they are non-axial. But when the ligand comes closer, it becomes clearer that the ligand is coming only towards the axial orbitals. So the axial get even more excited, like the two kids towards whom the ice cream seller is coming. They are going to get even more excited, like, yeah, the ice cream seller is only coming towards us. Whereas the 3 kids towards whom the ice cream seller is not coming, they are going to get like a little de-excited. They will be like, we just got excited in vain. The ice cream seller is not coming towards us. Okay, but they are not going to go to the level, that is the ground level in which they were before, because they are still a little bit excited, because the ice cream seller, they still thought that the ice cream seller is coming towards them. So they are still a little bit excited, but the excitation has dropped way below. Okay, so this is what is happening when the metal is approaching the ligand, or the ligand is approaching the metal. That is, when the ligand is approaching the metal, it is approaching towards the axial orbitals. So the axial orbitals, they get increased in energy. First of all of the d orbitals are increased in energy. Afterwards, when the ligand comes closer, it is seen that it is coming towards axial ones. So the axial ones are higher up in energy and the non-axial ones, they decrease in energy. Okay, so this gives rise to splitting, and this gives rise to the diagram that you see in this case. First of all, this you see the metal d orbitals, that is the dx square y square and the dz square, that is the pink one. These are the axial ones and these are the black ones. So these are the non-axial ones. First of all, when there were no ligands, all of them were degenerate. What does degeneracy mean? Degeneracy means that the orbitals are of equal energy. dxy, dyz, dzx, dz square and dx square minus y square, when there was no ligand present, all of them had the same energy. Then a ligand approached them from far away. So all of the 5 ligands, you can see, all of the 5 orbitals have increased in energy, right? Now when the ligand has approached even closer, it is seen that only the axial ones it is coming towards. So the axial ones, that is the dx square minus y square and dz square, they increase in energy, whereas the non-axial ones, they get lowered in energy. You can see that they are getting lowered in energy. So the axial orbitals, that is the dx square minus y square and the dz square, they are together known as Eg orbitals, and the dxy, dxz and the dyz, they are together known as the T2g orbitals. The barycenter that you see written in this diagram, it means that the average energy of the d orbitals. So barycenter is the average energy of the d orbitals. So the T2g orbitals are lowered from the average energy by 2 by 5 del O, and the Eg orbitals have increased in energy from the average energy by 3 by 5 del O. Here del O, this del O, it signifies the difference between the Eg and the T2g. Higher the difference between Eg and T2g, more will be the value of del O. Okay, so it's pronounced as del and O, del O. This is known as splitting of d orbitals, and this is for octahedral crystal field. Right now I am just talking about octahedral crystal field. That is, the ligands, they come closer towards the axial orbitals when they are present in an octahedral crystal field. For different crystal fields, the approach of the ligands and the orientation of the ligands is different. So the splitting will be different. This is specifically for your octahedral field. Next, we have a question related to that. So the question asks that relative to the energy, average energy in the spherical crystal field, the T2g orbitals in the octahedral field are A, raised by 2 by 5 del O, B, lowered by 2 by 5 del O, C, raised by 3 by 5 del O, and D, lowered by 3 by 5 del O. So we know that when the d orbitals, they are excited and then they split. So split, they give to give Eg orbitals and T2g orbitals. If this is the barycenter, then the Eg orbitals, they increase in energy by 3 by 5 del O, and the T2g orbitals, they get lowered in energy by 2 by 5 del O. So the correct option is B.